Okay, hello MathCounts friends. So in this video we're going to be going over the team round of the 2024 chapter competition. The chapter test was just released a couple days ago and we did the sprint and we did the target, so now we're going to move on to the team. So let's jump right into it. We did a pretty good job on the team round. We got 7 out of 10. We missed 3 out of the last 4 problems. Those are the hardest 4. And I'm going to go over all 4 of those, even though we got one of them right, because I think they're all really interesting problems. So let's go ahead and jump into it. This is the first one. So this is problem 7. And it says, how many ordered triples ABC of positive integers satisfy this equation? AB plus C equals 12. So basically, if you pick two numbers AB, they're going to have to multiply to give you something. Well, the lowest they could give you is 1 if they were both 1, and the highest they could give you would be 11 in order to allow C to still be a positive integer. So let's try to think of all the pairs AB that will give us something between 1 and 11. So maybe what we could do is say A equal to 1, and then we can list out what B is going to be along here. So B can be also 1. That gives us a product of 1, and then C will have to be 11. Or B can be 2, or B can be 3, 4, and I'm going to just put dot, dot, dot all the way up to 11. So we've got 11 possibilities for B if we select A to be 1. And now, what if I select A to be 2? Well, if I select A to be 2, we can still do 1, 2, 3, 4, and 5, because 2 times 5 is 10. If we went up to 6, we'd end up with 12, and C would have to be 0. But C has to be a positive integer, so we've got 5 possibilities here if we choose A to be 2. If we choose A to be 3, we can do 1, 2, or 3. And again, if we go up to 4, we run into an issue, so there are 3 of these. If we choose A to be 4, we could have B to be 1 or 2, but if we go to 3, we'll get to 12, so there's only 2 possibilities here. And then if we choose A to be 5, we can again do 1 or 2. If we choose A to be 6, we can only do 1, because once we get to 2, we're already up to 12. And then there's going to be 7 all the way up to 11, where we're going to have 1, 1, 1, 1, basically all on all those ones. So how many have we got altogether? We have, let's see, there's a 2 here. Okay, so we had 11, and 5 is 16, and then another 5 is 21, 23, and then we've got a bunch of 1s down here. How many of those do we have? From 6 up to 11 is 6 more 1s. So that gets us up to 29, if I'm not mistaken. 6 plus 2 is 8, and 2 is 10. Another 8 is 18, and 11 is 29. So yes, 29 is the answer here. So that was problem 7. Let's go ahead and move on to problem 8. This is problem 8. This one was really hard. I'm going to duplicate this figure down here. Maybe I will use the straight line tool. See how that works for me. So we've got a line there. We've got another line here, something like that. And then we've got the diagonal. So we've got a right triangle. And then we've got another line which is parallel, actually, to the other vertical line. Oops, I didn't draw that parallel, but that's okay. We're not going to worry about that. And then this one here. And we've got some right angles. It tells us that this is a right angle. It tells us that this is a right angle, and it tells us that this is a right angle. And in fact, that's how we know that this is parallel to this, is because they have these 2 right angles here. And then what it tells us is that this triangle ABD, which is this one here, it has an area of 18 centimeters squared. And it tells us that this other triangle down here has 14. So I'm going to draw those. I'm going to start using green because I think it's a little more visible. So 18 here and 14 here. And then what we want to know is the area of this triangle here. And they don't give us any side lengths at all, right? So it's a pretty challenging problem. What I like to do in this situation is I don't have any side lengths. I'll just start giving variables to some of the side lengths. So let's call the 2 legs of this smaller triangle W and X, and then we can call the hypotenuse Y, and we can call this other one over here Z. And then maybe we'll call this one A. I run out of letters. So from here over to here, we'll call that A. Okay, so the next thing to do is to start thinking about whether we have some similar triangles. And it turns out that we do have a lot of similar triangles here. Because if you notice, there's a couple angles here and here that add up to 90 degrees. And there's also this bigger angle here. It also adds up to 90 degrees with this angle because these are complementary. And so we can say that this angle here, this smaller angle in the triangle, is equal to this smaller angle here. And of course that means that this one, since it also adds up to 90 degrees with this one, and these two add up to 90 degrees, that means that this angle is equal to this angle. And of course this angle adds up to 90 degrees with this angle, and so this one is the same as this one, is the same as this one, and this one is the same as this one. So we've got, and I guess this one over here is like that. So we've got a bunch of similar triangles. This triangle that's area 14 is similar to the one that's area 18, and it's similar to the one that we're trying to figure out the area of, and they're all similar to this big triangle that makes up the whole figure. All right, great. So let's see. How am I, now maybe I can start looking at the ratio of some of these sides. I don't know how long any of these sides are, but maybe I can figure out the ratio between some of these sides. So let's look at x to y. Let's look at that ratio, x over y. Well, one thing I know is that this ratio has got to be equal to y over z. So that's got to be equal to y over z because of similar triangles, right? There's similar triangles here. And I also know that if I have two similar triangles and I know the ratio of their areas, the ratio of the corresponding sides is going to be the square root of that ratio. So x divided by y, which is what we have here, is going to be equal to the square root of 14 divided by 18. And I can simplify that to be the square root of 7 over 9. Okay, great. So that's really good. Now, from that, I can figure out that y is equal to square root of 9/7 times x, and z is the square root of 9/7 times y, which is the square root of 9/7 times x. So z is really just 9/7 of x. All right, and so now I could just label this one x, this one square root of 9/7 x, and this one 9/7 x. And I can also use the Pythagorean theorem to figure out what w is, because I know, at least I can figure it out in terms of x, because I know y in terms of x, and I know obviously x in terms of x. So I can do, the Pythagorean theorem would tell me that y squared, which is 9/7 x squared, so 9/7 x squared, minus x squared is going to be equal to w squared. And so 9/7 x squared minus x squared is going to give me 2/7 x squared. So w squared equals 2/7 x squared. And of course I can take the square root, and that just tells me that w is equal to square root of 2/7 x. Okay, so now I know all these in terms of x, and I can figure out this last one in terms of x also. The way I'm going to do that is I'm going to say that the ratio between z and a has got to be equal to the ratio between w and x. Okay, so w divided by x has got to be equal to z divided by a. And maybe I'll cross multiply, and this tells me I want to make a little bit more room, so I'm sort of running out here. Let's make some room here, because I've got everything I need from that over here. So this tells me that z was 9/7 x, so this is really x times 9/7 x, which is 9x over 7, I guess. So that's xz. I'm sorry, it's got to be squared now because I've done 9/7 x times x, right? That's zx. So 9x over 7. That's xz. Xz has got to be equal to wa. So that's got to be equal to w is square root of 2/7 x. and then that's going to be times A. So A, I guess I just need to divide this part, divide both sides by this part to get A all by itself. And so if I do that, let's grab another color real quick. If I do that, I'm going to get A is equal to, let's see, the x is going to cancel with this x, so I've got 9x over 7 times the square root of 7 halves. So I'm going to get the square root of 7 halves times 9x all over 7, I guess. So that's A. All right, now I can find the area of this triangle we're looking for in terms of x. I still don't know what x is, but I can take x times A, because I know A is this. Actually, x times A I can just do really easily. X times A is just this, right? I multiply both sides by x. And now if I divide by 2, I'll have the area of the triangle, because the area of the triangle is x times A divided by 2. So if we divide by 2, this is going to be, instead of a 7 here, we're going to have 14 here. All right, so this thing here is the area of my triangle, but I still don't know what x is. Okay, so how am I going to figure out what x is? Well, actually, you know what? I think I have maybe a better way to do this. Yeah, I think this was kind of, I think I took you guys on the wrong turn here, because I already know the ratio between w and x. And so that should give me the ratio of that should be the square root of the ratio of the area of these two triangles. I think that's going to be a better way to do it. So let me apologize for taking you down a wrong track there, but let me, I mean, we could have solved for x because we know these triangles. We could have solved for x that way, but I think this is going to be even cleaner if we do it this way. So let's see. So let's go back here. I'm going to fix my square root here. Okay, so what we know is that 14 divided by x is going to be equal to the square of w divided by x. So that's, is that right? Let's see, 14 divided by x is going to be, I'm sorry, what did I say? 14, x. This x is different than this. Let me give this thing a name. I don't want to use x again because x is this side length, so let me fix that. Let's call this area t for triangle. Okay, so 14 divided by t is the ratio of these two areas, and that should be the square of the ratio of the two shorter legs. So that is w squared divided by x squared. And this we know because w is square root of 2/7 x. So w squared is 2/7 x squared, 2/7 x squared, and x squared is just x squared. That's really nice because that's just going to cancel out. And we've got 14 over t is 2 over 7. Okay, this is great. We can just cross multiply here. That gives us 2t equals 14 times 7, which is going to be 2 times 49. I'm going to do it that way because now I can cancel the 2's, and I just have t equals 49. Okay, so 49 is our answer. That's the area of the triangle. All right, great. Sorry, I led you guys on a wild goose chase. It would have worked out okay, but I think this was a nicer way to do it. Once you have w and x, that works out even better. All right, great. Let's go to the next one. So this one you guys got right. This one was problem 9, and it says the figure on the left shows a chain that consists of 7 links. 2 randomly selected links are cut open and removed from the chain. The figure on the right shows one possible outcome in which links 3 and 7 were removed. Okay, so there was a link 3 here that got taken out, and there was a link 7 here that got taken out. And it left 2 separate chains. So if we take those ones back out again, you can see that there's 2 chains left. And the question is, what is the expected number of separate chain segments that will remain after 2 randomly selected links are removed? Express your answer as a mixed number. So One thing is you have to know what it means, the expected number. What's the expected number of chain segments? So there are going to be some possibilities where the number of chain segments is going to be 1. You know, for example, if I remove the first and the last link, there will just be 1 chain segment. There will be some cases like this where the number of chain segments will be 2. And there will be some cases where the number of chain segments will be 3. So if I remove chain segment 2 and 6, for example, I'll have 3 chain segments because there will be the link 1 will be all by itself, and then 3, 4, and 5 will be together still, and then link 7 will be all by itself. So we'll have 3 different segments. So those are our 3 possibilities, but they're not equally likely. To find the expected number of chain segments, you have to take the probability that you're going to have 1 chain segment times 1 plus the probability that you're going to have 2 chain segments times 2 plus the probability that you're going to have 3 chain segments times 3. And if there was a probability that you would have 4 chain segments, for example, you'd have to keep going. But since those are our only 3 possibilities, this is how you compute the expected value. So this is going to be the expected number. Expected number. Now, of course, that's just what the expected number means. It's a mathematical definition. It's the weighted average based on the probabilities. You wouldn't actually expect to get that number of chain segments because this number of chain segments is going to be a mixed number. You're going to always get an integer, right? So you can't expect to get exactly the expected number. So it's a little bit, the expected number is kind of the number that's, it's really just the weighted average weighted by the probabilities. So it's the best guess as to how many. It's going to be close to the number of chain segments usually, but it's not going to be equal to it because it's not even going to be an integer in general. Okay, so we need to figure out these 3 probabilities. What's the probability that it's going to be 1 chain segment? What's the probability that there's going to be 2 chain segments? And what's the probability that there's going to be 3 chain segments? And I tried a couple different ways to do this, looking at like n choose k and things like that. And you know what? I just decided that maybe the easiest way to do this is just kind of brute force it a little bit. So let's take a look at this. You could have the 2 chain segments that are taken out to be next to each other, or they could be spaced 1 apart, or they could be spaced 2 apart, or they could be spaced 3 apart, and so on. So maybe let's consider each of those cases separately and split it up into those cases. So if I say that they're next to each other, I could either have the ones removed to be these 2, 1 and 2, or I could have these 2, 2 and 3, or these 2, and so on, right? These 2, these 2, these 2. So maybe what I could do is I could say, let's say what the first chain segment is. So maybe I can make a chart. What the first removed is along this axis. And then going down, I could say, what is the spacing, right? The spacing between the 2. So for example, spacing of 1 means that, you know, it's link 2 minus link 1. So if I say the first removed is 1, that's going to be 1 and 2 with a spacing of 1, right? So if I do that, so I'm going to make a table, I guess. Maybe I'll make some room here so I can put those numbers. I'll just remember that this is the first removed segment. Or I can label that over here. This is 1R for first removed. So this could be 1 or 2 or 3 or 4 or 5 or 6, right? I can't have 7 because there's not 1 after it. So those are the possibilities for the first removed, FR. And then the spacing could be 1 or 2 or 3 or 4 or 5. I guess there's a 6 too. There's only one possibility there. I'm running out of room, so we'll do that one separately. But let's just make this chart. So so we're really going to just brute force it here. So if you say that the first removed is 1 and the spacing is 1, that means you've taken out these 2 chain segments. And if you do that, you're going to have only 1 chain segment left. So I'm going to put a 1 right there. And if I start with the second one, that means I'm removing 2 and 3. and there will be 2 chain segments, and same thing with 3 and 4 and 5. But if I start with number 6, that means I'm taking out 6 and 7. There's only going to be 1 chain segment. So now let's go to a spacing of 2. If I start with 1 and there's a spacing of 2, that means I'm taking out number 1 and number 3. And that's going to leave 1 chain segment, which is just link 2, and another chain segment, which is links 4 through 7. So that's going to be 2. But then as I go to the first one being 2, now all of a sudden I have 3. And the same thing here, and the same thing here. If I start with 4 and I take out 4 and 6, there will be 3. But as soon as I get to 5, it'll be 5 and 7 that get taken out. Then it'll only be 2. And now let's say that I have the spacing of 3. So the first one is going to be 1 and 4. If I do that, it's going to be 2. But as soon as I go over here, it's going to be 3 again, and 3 again, and then 2. And I can't start with 5 and have a spacing of 3 because that would take me up to 8. And then for 4, again, I'm going to have 2 and 3 and 2. That's kind of the patterns. The first one is always 2, and the last one is always 2. Except, I mean, at least it wasn't the case when they were next to each other, but when they're spaced out, that's what I get. And then the 3 in the middle. And then with a spacing of 5, that's going to either be 1 and 6 or 2 and 7. In either case, I'm going to get 2. 2 and 2. And then the last case has got a spacing of 6 and the first one obviously of 1. So if I do that, that means I'm taking out link 1 and link 7. That's going to give me 1 link at the end. It's just going to be the ones 2 through 6. So now I guess I just, to get the probability of 1, I just count up the number of 1s and divide by the total number of possibilities. So there's 1, 2, 3 1s. Basically, there's 3 pairs you can take and have it just leave 1 chain segment. And those are taking chain links 1 and 2. That would just leave you 1 segment. Or take links 6 and 7. That would just leave you with 1 segment. Or you take links 1 and 7. That will also leave you with 1 segment. So that's 3 out of, so probability 1 is 3 out of something, right? So the number of possibilities. So I guess now I can use n choose k, or I can just count up how many of these there are, but it's 7 choose 2 is the number of ways. So that's going to be 7 times 6 divided by 2, which is 21. Hopefully this is 21 if I do, let's see, 6 plus 5 plus 4 plus 3 plus 2 plus 1. That'll give me 21. So there's 21. So this is 3 out of 21, or 1/7. The probability of getting 2 chain links, let's see, we can just count up how many 2s there are. There's going to be 4 up here, and then there's going to be 4 down, down here, and there's going to be 4 along this diagonal here. So 4 plus 4 plus 4 is going to be 12. So this is going to be 12 out of 21. And hopefully the rest is 21 minus 15 is 6. And yes, indeed, there's 1, 2, 3, 4, 5, 6. So there's 6 out of 21 is going to be this probability here. So now, let me make some room down here. I don't need this table anymore. We can just figure out what this expected value is. All those things can be simplified because they're all divisible by 3. Those fractions, the numerators and the denominators, are all divisible by 3. So we can simplify this a bit. So let's do that. So we've got 1/7 times 1. I don't need to times 1. So then we have plus 4/7 times 2, so I'll just put 4 times 2/7, plus this one will be 2/7, 2 and then times 3, so 2 times 3/7, and that's going to be my expected value. So what is that? So it's how many 7s? I've got 6 plus 8, so it's got 15/7. 15/7. That's my expected value. They want it as a mixed number, so we're going to say that that's equal to 2 and 1/7. So that's the expected number of chain segments, 2 and 1/7. And we got that one right, so good job, you guys. Now, again, obviously, it's impossible to get exactly 2 and 1/7, but that's going to be the number that's, on average, closest to the number of chain segments, no matter how you pick it. So there you go. It's most likely that you'll get 2 or 3, I guess, right? Because there's higher probability of those than this one. But it's kind of the weighted average of the possible number of chain segments is what's called the expected value, or the expected number. All right, great. That was number 9. And now we're going to go on to number 10. So this one's number 10 here. And this one was a pretty tricky one. It says Carolyn has 2,024 pennies in a display case. Of course, MathCounts always likes to use the current year in their problems, and the current year is 2024. So she has 2024 pennies in a display case. And first she replaces every 8th penny with a nickel. All right, you're allowed to use a calculator. So we can kind of say, all right, if she has every 8th penny, 2024 divided by 8 is going to be 253. So there's going to be 253 of these that she replaces by a nickel. So how many pennies does she have? She starts out with 2024 pennies. And then we have to subtract 253 because those get replaced by nickels. 253 here. Okay. Now, it says after she does that, she replaces every 11th coin with a dime. So how many coins is she going to replace with a dime? We can just take 2024 divided by 11, and that's 184. Okay, so 184 of these are going to be replaced by dimes. 184 dimes now. But how many of those were nickels, and how many of those were pennies, the ones that she replaced? Well, let's see. I guess since 8 and 11 are relatively prime, they don't have any common factors. It's going to be every 11th. It's going to be every 11th nickel that gets replaced by a dime. So we had 253 nickels. If we divide that by 11, we get 23. We're lucky that all of these are integers, because it makes it easy. We don't have to worry about, was it the first one or this? We just know that there's going to be 23 of these nickels that get replaced by dimes. So we can subtract 23 nickels, and we have to subtract some pennies as well. All the ones that we replaced, these 184 coins that got replaced, 23 of them were nickels. That means the remainder were pennies. So let's do that. 184 minus 23, that's 161 pennies that have now been replaced, in addition to the 253 that were replaced originally. Actually, no, not in a... Well, yeah, in addition, right? Yeah, so minus 161. So this is now the number of pennies we have, and this is now the number of nickels we have, and this is now the number of dimes we have. And then she does one more thing. She replaces every 23rd coin with a quarter. Okay. So 23 is also relatively prime with 8 and 11. And in fact, fun fact, 23 times 8 times 11 is 2024. So if you happen to know the prime factorization of 2024, this might have been a little bit useful for this problem. They always try to make that a useful fact. A lot of times they do, every year. So what's going to happen if you replace every 23rd coin with a quarter? How many of those are going to be dimes? Well, we had 184 dimes, and if we divide by 23, that's going to be 8 of the dimes that are going to be replaced. So we're going to subtract 8 dimes. And then let's see, how many of the nickels are going to be replaced? Well, there's actually one coin of these 2024 that gets replaced every time. It's the very last one, because 2024 is divisible by all three of these numbers, because that's the factorization of 2024. And so the very last coin is going to be replaced every single time. So let's see. So how many of the dimes are going to be replaced? I guess we can take our 184. No, not our 184. What was it? We had our 2024 divided by 23. That was 88. Our 88 coins that were replaced. We said 8 of them 8 of them were dimes. And if we divide by, but one of those dimes had already been replaced from a nickel. So we can, if we divide by 11 instead of 23, oh no, I'm sorry, we take our 23 and we divide now by 11. So there were 88 coins that were replaced, right? That was our 24 divided by 23. There were 88 coins that were replaced. If we divide by 11, we can figure out, oh wait, we did that. We figured out how many of the dimes were replaced. Now, if we divide by 8, we can figure out how many of the ones that were nickels originally are replaced, and that's 11. But one of those was already replaced by a dime. So it's really only 10 nickels that we're losing. So we subtract 10 here. And now all the rest of our 88, oh yeah, we got our 88 quarters here. All of the rest of our 88 quarters, if we don't count this 8 that were dimes and the 10 that were nickels, all the rest of those 88 were pennies. So 88 minus 8 minus 10 is 70. So this is now the number of pennies we have, this is now the number of nickels we have, this is now the number of dimes we have, and this is now the number of quarters we have. And what are they asking? They're saying, what is the new value of the coins in our display in cents? Okay, so we just plug this into our calculator, I guess. We do the number of pennies, which is 2024 minus 253 minus 161 minus 70. And then we add 5 times the number of nickels, which is 253 minus 23 minus 10. And then we add to that 10 times the number of dimes. I need a times here and here. 10 times the number of dimes. The number of dimes is 184 minus 8. And then we're going to add to that 25 times the number of quarters, which is 88. And that gives us 6,600. So let's see. 6,600 is the answer. How about that? So we got our calculator and we figured out the answer to this one, 6,600 cents. Okay, so that one was pretty tricky, but they made it a little nice by making sure that all of these, there was a lot of things that evenly divided. So 8 and 11 and 23 all evenly divided into 2024, and since they were all relatively prime, it made it a little bit easier to manage which ones were being replaced. It was still a little tricky when it came to replacing the quarters. You have to keep track of which ones were already replaced, but that's how you do it. So we got pennies, nickels, dimes, and quarters. 6,600 cents in the end. Okay, well, I hope you guys all enjoyed that video. Hope you guys learned something, and I'll see you guys on Wednesday. All right.